All right, then for the last speaker in our session, I would like to introduce Ognjen Maric. He got his PhD from the ETH Zurich in 2017. Afterwards, he worked at Digital Asset, building Canton, a privacy-enabled protocol for atomic transactions across mutually distrusting parties. Afterwards, he joined Dfinity in 2021 and is now working on the Internet Computer Protocol. His main focus on work is on formal verification, as well as distributed systems and security. And today, we will be hearing something about how to build fast and reliable peer-to-peer without breaking the memory budget.
Thanks, Richard. I guess it's probably the last talk of the workshop, so I'm never sure if that's a good sign or bad sign. So this is work on some work that we've been doing over the last, say, year and a half. So it's actually worked with a lot of people, so now it's implemented. So there's a lot of people from research, Dfinity, now also from engineering. This thing is actually running, and let me give you an introduction what it's all about. So it's going to be a pretty technical talk. So if you have a blockchain, the first question that people ask is, what's your consensus? So you need to have consensus generally in blockchain, and if you have consensus, you usually have some kind of peer-to-peer broadcast, especially in sort of algorithms that have deterministic finality, so something like based on more standard 2/3 assumptions like proof of stake or whatever. So if you look at the Ethereum finality gadget paper, they'll say, okay, you need to broadcast something. If you look at the Polkadot paper, they also broadcast something. If you look at the Internet Computer, so this is the blockchain that the Dfinity Foundation is working on, there's also, unsurprisingly, there is broadcast. And in general, you want this broadcast to be reliable. So if you don't actually manage to broadcast the message, so if some peers don't receive a message to broadcast, your algorithm can get stuck. Broadcast is pretty simple, right? There's you open any textbook on distributed computing, and you're going to find a ton of broadcasts. So you're going to find pick one. It's a pretty simple thing, right? You just send messages to all of your peers, and you might need to retransmit, but that's pretty much it. So it's textbook stuff, should be a solved problem. You might want to optimize performance, but in principle, reliable delivery should be solved. But it turns out that simple problems are actually sometimes not so simple. So if you want to be reliable and fault tolerant, and you also want to have bounded memory, it turns out that this is a little bit difficult. Let me show you why. So let's start with a simple client-server scenario, so no blockchain. You just have a server. You have you have the app that's actually trying to send something to the client. And it uses the networking layer, right? So what happens if at some point the network fails, right? So you cannot send messages. So you have three options. So the first option is just drop the message, okay? Second option, you buffer something somewhere. But the danger is that if this app keeps producing data, your buffer might grow unbounded. And the third option, which you normally do, is you just backpressure. So you say, stop producing data. The client is not there anyway, so there's no point in producing any data. Right. Okay, now if you move to a peer-to-peer scenario, such as the scenario you have in consensus, okay, same picture. Now let's say one of these links fails. So what do you then do, right? Well, you're actually stuck with the same three options. Right? These are kind of the things that you can do. Right? So you can either drop, you can buffer, or you can backpressure. And all of these options actually suck. So the first option is if you drop messages, you're not reliable. And as I said before, if you're not reliable, your consensus algorithm generally will get stuck. So that's not a good idea. Option number 2, backpressure. So that worked for the client-server scenario, but here it actually doesn't work anymore, because this means that if one of these clients fails, essentially you stop the whole algorithm. So this is also far from ideal, right? This means that you're no longer fault tolerant. This is and the whole point of having a consensus algorithm is to be fault tolerant. And the third option is to buffer. So this might work for a while, actually. I guess, conceptually, this is what some blockchains do. But the problem is if you have a really high throughput protocol on the left, it's going to be producing a lot of data. So pretty quickly, you're going to run out of memory. And this is essentially going to be like a denial of service attack, because you're going to crash your senders. So your consensus is going to get stuck again, so you're again not really fault tolerant. Okay, so there's no real way to win this game. So if you can't win the game, you have to change the game, Right? So this is what we do in our solution. We say, okay, we don't have reliable broadcast. We have what we called abortable broadcast. And what's the key idea here? The observation is essentially that in general, protocol messages, they tend to become obsolete, for example, through checkpointing, as the protocol executes. So the idea then is to make use of this, and we add an explicit abort call to our networking layer that says that a message is no longer needed, it's become obsolete, and what we can then do is we can essentially just buffer unaborted messages. And this way we get all of the stuff that we wanted, so we get to be reliable, at least for unaborted messages. We get to be fault tolerant because there's no backpressure, so the protocol can continue running. And we also have bounded memory usage because we don't have to build unbounded buffers. So this is the high-level idea. And in the rest of the talk, so there's an assumption, and the assumption is that the number of unaborted messages is actually bounded at every point in time. So it means that if you're doing checkpointing, essentially you have to do checkpointing on a regular basis. But this is a pretty realistic assumption. So I'm going to run you through the rest of the talk. So I'm going to talk about this abortable broadcast. I'm going to talk a little bit more about how the interface of this looks like more precisely, like what are the assumptions, what are the guarantees. Then we look at how we implement abortable broadcast. So we have an algorithm how to do it practically. And then I'll briefly touch on some evaluation and related work. So we start with the interface and the assumptions and guarantees. Okay, so here's the setting. You have the high-level protocol on the top. It wants to send some messages. You have the P2P at the bottom. And you have a send side and a receive side. So you can either, it's a peer-to-peer protocol, so it can be either a sender or receiver. So let's say you have some kind of message processor here in the high-level protocol. And this thing is going to add or delete messages to some pool of messages that's currently being sent. Once you add a message to the send message pool, there's going to be, the interface is basically that you have to notify the P2P part that you've done this. So there's an event saying I've sent a message or I've deleted the message, which means that I'm aborting sending this message. I no longer need to send this message. Okay, and then on the receive side, the interface is that you have some receive logic in the P2P that's basically going to add and delete messages as it receives them to some received message pool, okay? And then the message processor here from the top, it can just process these messages asynchronously, so it can pull stuff from the received message pool. Okay, so that's kind of the interface. You're sending and aborting, sending messages from the send message pool, adding them to the received message pool. That's the whole thing. Now, the assumption is, again, that this message send message pool here is bounded in size. So the number of messages has to be bounded, and the size of messages also has to be bounded. And with that, we can provide the following guarantees. So if you have an honest sender here, that's, let me move it this way maybe. So the higher level protocol on the honest sender is trying to send something, or it can abort something. And on the receiver end, you're adding and deleting messages to this received message pool. So the guarantees are as follows. If you send a message, if the higher level protocol sends the message, you're eventually going to receive it. You're eventually going to add it to the received message pool, unless you abort it. If you abort it, who cares? Then if you send a message, you don't abort it, then the message is going to be received timely. So as long as the network behaves, so if the network is kind of doing what it should be, in those periods, we're going to deliver messages timely. And finally, what I mentioned earlier, both the P2P and the received pool actually use bounded memory. So these are the three guarantees that you get from our implementation. Okay, so let's see how we implement this. So this is what we want to implement. Let's see how we implement it. So now the P2P part now becomes a bit bigger. So this is, again, I'm going to give you like a conceptual explanation of how we implement this. There are a lot more details actually how to do this in a more efficient way, but this is the general idea. So you have some kind of transport connection to the peers. So these are going to be like quick connections between peers, but you have like a connection to each peer. So this is our assumption right now, that you have full connectivity. So there are no overlays or anything like that. Now, when you send a message, or when the high-level protocol sends a message, and you receive the send or abort message event, what we keep in here is some table of active messages. So this table is going to be bounded because it's going to correspond more or less to this send message pool, which is bounded. And based on this table, we're going to send messages to each of the peers. On the other end, the receive end, we have like one such table for each sender. Okay, and essentially we synchronize this table with this table eventually using this this transport. And the catch is that so once you have receive a message here, you can then add it to the message pool. And once the message is no longer in any of these tables, you delete it from the message pool. And the trick is that you have to allow for congestion. So if there's a congestion in one of these pipes, then you don't need to slow down table updates here. You just somehow slow down like sending those table updates to that individual peer. Okay, so now I'm going to look, I'll tell you a little bit more about the, oh, great. I can delay this by 1 hour, by no longer. Good. So you can hack me apparently and steal my tokens because my Chrome is out of date. Okay, so let's look at this table structure in a bit more detail. So the table consists of these slots, and there's a bounded number of slots. So let's say we have 5 messages total. And each slot has some content, which can be empty. So here we have a slot with an empty content and has a version. And effectively, whenever you make a change, you just bump the version up by 1. Okay, and since we have a bounded number of slots, we are bounded, at least in this part. Like I need to argue a bit more why we're bounded overall, but hopefully you can see that we're bounded at least here. So when you send a message, you have a new message F. What you do is you search for an empty slot, and there's an invariant that such an empty slot must exist. So you find, let's say, this one here. You stick the new message F, and you bump the version up to 5. Okay, so pretty simple. And then when you delete a message, you just find the corresponding slot here. You set it to empty and increase the version. Okay, and let's say now we have some slot table like this on the sender side. So here we added A, B, C, D, E, F. So we added into slots 0, 1, 2, 3, 4, 5. The versions were 1, 2, 3, 4, 5, and so on. And then we've done some removals. So hopefully you can see that the version 7, we removed something for slot 1. So this is why the slot is empty, for example. And the idea is now that we basically, what we do is we just stream these events, these changes, to the receiver. So we can, in the simple version, you can just send like one, let's say, UDP message or something like that. It's not quite what we do, but you can think about it that way, to the receiver. And then the receiver has like essentially an eventually consistent view of the sender side table, even under congestion. And for example, if now the receiver receives this message that we're adding G to slot 5, you can see, okay, in the previous version, slot 5 had version 6, but now we're receiving a message at version 10, so we can actually overwrite this. So we can add the changes. Now the big trick is that you don't actually need to transmit all of this stuff here. Like if there's congestion, if there's no congestion, this is what you're going to be doing. You're just going to be streaming changes. But if there's congestion, you can see that actually some changes become obsolete. So you see that this change here, like where we added B, it's actually become obsolete in step 7, because in step 7, we removed B from there. So there's no longer need to actually transmit this change or this change from step 2. And similar for these things here, we don't actually need to stream these events. So if you're lucky, if everything is going okay, we just stream these events. If not, we kind of remove them, and we only have a bounded number of events that we need to stream. They can all be deduced from this table. And we get 2 essentially properties. One is that for the table elements that have not been overwritten, we don't remove those. So like eventually we are going to send this message unless we abort it also. So we will deliver this reliably. And the other thing is, since we don't need to retransmit all of these events, it's going to be just a bounded amount of events or number of events that we need to retransmit. So we can also be timely, because we have just a bounded number of things we are retransmitting. Like retransmitting a message takes, when the network is behaving correctly, takes a constant time. So effectively, we can always send all of these messages in some constant time once the network behaves properly again. Okay, so this is the high-level intuition. The implementation, as I said, is more complicated. One of the more important optimizations is to optimize the bandwidth. So what we send, in general, for large messages, we don't send the whole message. We just send an advert, so like a short description of the message. And then here on the right, the other peers they receive. For example, we can have an advert for a block, which can be like 4 megabytes. So instead of sending the block directly, we just send the advert for the block, and the other peers, they request the block if they need it. So this can be very helpful because many messages are relayed, so blocks can be relayed, so you don't need to like send 4 megabytes, or you don't need to receive the same 4 megabytes, dozens of times. And some messages may be interesting at some point, but for example, the receiver might not yet be able to process them. If it's processed in the blockchain, it's fallen a bit behind. It may not want to download large messages immediately. It may only want to download them later. And in general, this decreases latency, it saves bandwidth, and increases throughput. But it does make our interface a little bit more complicated, but I won't get into that. Okay, so yeah, get the block delivered. Forgot to click that one. Okay, and quickly about the evaluation and related work. So a bit surprisingly, but there's not actually so much in terms of guaranteed message delivery with bounded memory. So if you look at the original PBFD paper, they actually do this, or if you look at Castro's thesis, but they have like a very bespoke retransmission mechanism, and they're using stuff like unreliable transport like UDP, and they actually address this issue explicitly of keeping the memory bounded. Now, if you look at stuff like Bitcoin or Ethereum 1.0, so there's no checkpoint in general. So in general, you'll be using you need to retransmit the entire blockchain since Genesis. So there's no unbounded memory, or there's unbounded memory, or rather, there's no bound on the memory. But in practice, it's not that big of a deal because the throughput is so low. So the entire Bitcoin history is still like 600 gigabytes. So this is still bearable. And if you look at GossipSub or its implementation libp2p, so this is a P2P implementation that's used widely by many now blockchain projects, so Ethereum 2.0, for example, Polkadot, Polygon, Mina, and so on. So they do explicitly provide you with bounded memory, but they don't give you any delivery guarantees. So if you want delivery guarantees, you have to implement retransmission on your own on top of this, right? Whereas our solution just has sort of reliable delivery built in. So to illustrate this point, here's an experiment that we ran where we have 31 nodes, and then after 2 minutes, so we're sending artifacts or sending messages constantly, and after 2 minutes, we crash the nodes for 30 seconds. And here with GossipSub, you see that the nodes that were crashed, so they actually don't receive all the messages, so they have lower messages received than the operational nodes. But here with us, actually, they catch up with essentially the operational nodes quickly. So after the restart, right? And so performance-wise, we also compared ourselves to GossipSub, so we are kind of competitive or even slightly better in terms of cumulative latency. So you see that here, for example, we reach like the 99th percentile of latency already at, I don't know, maybe 300-400 milliseconds, whereas GossipSub takes a little longer. Now, this is with 31 nodes, so to be fair to GossipSub, it's meant for something different. So we don't implement overlay networks yet, they do, which means they would perform much better once you have a larger number of nodes. But in our subnets currently, we don't have more than 30, or we have 40 nodes at most. So for our current purposes, this is okay. And this is without actually saturating the links. So we're like below link capacity when running these experiments. Okay, so to then summarize, what are the takeaways? So if you want to claim you're truly Byzantine tolerant, you also need to make sure that you don't crash your nodes by running out of memory. And conversely, if somebody claims that their system is Byzantine fault tolerant, maybe ask them how they ensure that they don't run out of memory. If you need reliable delivery, that's actually not entirely so simple when bounded. So I think the algorithm I showed you, it's reasonably simple, but we haven't actually seen this in the literature before. And our solution can achieve sort of all three, so be fault tolerant with bounded memory and ensure reliable delivery. We haven't sold everything, so we're also happy to collaborate on many topics in terms of networking in particular. So one topic is, of course, better bandwidth utilization. So as I said, we don't have overlay networks, for example, at the moment. So it'd be interesting to see how we can incorporate those or something like error correction codes while keeping delivery reliable. Also, right now, we don't handle input messages like that well, so I didn't go into input messages, but this also touches on the networking part. So for example, right now you can use the internet computer, for instance, to serve something like Reddit. You can actually serve it fully from the internet computer, like people built this. You can upload up to, say, like 2 megabytes per second, but you cannot build like a TikTok. If you want to build a TikTok on an internet computer, that won't work because you need to upload all these huge videos, and this won't work. But we would like to get there at some point. So we would like to figure out better ways of handling these input messages, and we have some work on that as well. And what this work hasn't touched on is also resilience to volumetric attacks. So we've seen talks on Cyan and so on, like yesterday, for example. So it'd be interesting to see how we can prevent, denial of service or distributed denial of service attacks. And it's particularly interesting if you have not only outsiders, but you also have like insiders that are attacking you, right? If the other nodes actually try to attack you, like how do you defend against that? And yeah, I'm pretty much done there. So I'm just going to drop a link here if you're interested in developer grants and so on. So I didn't touch on like what the internet computer does and why it does what it does, and all the features. So we have, threshold signatures, and we have some pretty unique features like smart contracts can actually make HTTPS out calls to other blockchains and so on. But yeah, if there are any questions, I'm just going to leave this on the side. Thanks.
Great, thank you very much. Do we have questions from the audience? If not, then, oh, I saw something.
Okay, wonderful talk. Thanks. Can you say something about how the mechanisms you explained map to example application requirements? Like, so you look at specific scenarios where you have around about 30 nodes.
Mm-hmm. Yeah.
And
right,
what kind of application scenarios are suitable to that? And is there also space beyond where you would say this needs further work?
Right. So it's a good question. So I guess it's a trust issue, right? So essentially, or it's the amount of nodes that you have. If you have a typical blockchain algorithm, like these nodes usually do repeated work, right? So if they do validation, so they're running the same state machine. So the more computation you're doing, the more expensive this is going to get. And now I guess the question is like, where is the sweet spot between doing too much computation and having like higher assurance or lower trust assumptions? So we have like flexible deployments in these regards. So we have like our default, if you just upload something to our blockchain, like you're going to get a 13 node shard that's going to be executing your code. So you can go to like a higher assurance one, which is more expensive, but there we have 30 nodes. And then we have a special subnet, which is actually, I think I have it somewhere here. So we have these different subnets, right? So these are the different shards, and they're actually of different sizes. And one of them is sort of this governance subnet, which is the brain of the whole thing. You can upgrade and change everything. So that's currently running like 40 nodes. And this is probably the one that we would like to get up to something higher, to something like 100 or a couple of hundred nodes. But it's sort of a tricky question also, like if you think about, how decentralized do you want to be? So if you think about stuff like Bitcoin, in principle you have a lot of validators, but then you also have these like pools that are actually controlling quite a bit of the system. If you look at them kind of as one entity, so you have maybe only a few entities that are controlling the same thing. So it's not really, there's not like a clear-cut answer, but I hope I answered some of your question.
Absolutely, thanks a lot.
I also have a question. So you were saying not too much about the transfer protocol, but considering that you're assuming that everything just works, even if congestion happens, for example, is there something that the transfer protocol could do for your idea that makes your life easier?
So yeah, we do use a transport. So we use Quick in production. The reason we use Quick is that we don't run into, like, we might run several P2P, so several clients here. So we have like the consensus client. We have, for example, also the threshold cryptography, so threshold ECDSA or Schnorr signatures. So we don't run into stuff like head-of-line blocking problems. Then also, we don't need to actually implement our own retransmission at the network layer or the transport layer. So Quick takes care of that. But we do retransmission. So essentially, we have some send tasks that try to send something to Quick, and then if the buffer is full, you kind of you block on that. I think the Quick, I think it solved most of our problems for the time being. But yeah, if you have any like concrete ideas what protocols might improve things there. I mean, I know the talk that you mentioned yesterday. So if you could like fine tune maybe some of the parameters, that might be something that could help. Yeah, I'm not sure. So I'm not a network person myself, so I don't know how much flexibility Quick provides you in that regard.
Thanks. Do we have further questions? All right, doesn't seem to be the case. Then we thank our speaker very much.
Thank you.